force systems. And in the last class, we saw a system of coplanar forces or couples. Now today, we will look at another system where finding an equivalent is fairly straightforward, and this is what we call as parallel force systems. So parallel force systems would mean that, let us say, on a body or whatever your system is, there are n parallel forces. So all the forces which are acting on the body, they are parallel. So what we do is, because they are all parallel, without loss of generality, let the forces be parallel to the z-axis. Why do I say without loss of generality? Because we are free to choose our coordinate system the way we like. So what we have done here is, we have chosen our coordinate system such that the z-axis is either parallel or anti-parallel to these forces. So that means these Fi vectors, we can write it as Fi scalar with a unit vector A, and Fi can be either positive or negative. If Fi is positive, then we are parallel to the z-axis. If Fi is negative, we are anti-parallel to the z-axis. So now we also include the couples. And what type of couples will we include? Couples which are formed by such forces. Such forces means forces which are parallel to the z-axis. And what this will mean is that the m couples which we include in our system, they are in a plane parallel to the z direction. That is, we have C1, C2, Cm couples which have only I and j components. So once again, the system of parallel forces which I am talking of, that means the system of parallel forces, this includes A forces F1 up to Fn, such that each of these forces Fi is equal to Fik, and couples C1 up to Cm with Ci along x and y directions. So having done this, now for this system, the resultant at any point, and let us say we choose this point as the origin, will consist of, as we have seen, for a general system, the resultant consists of two parts: a force, which we say Fr, and this will be equal to sigma I going from 1 to n, F sub I scalar times k, because now all the forces are parallel to the z axis. And the second part will be a couple, and since we are saying this is from the origin, first of all what we'll have to do is, let's calculate the couple because of each of these forces. So the couple because of each of these forces will be xi I plus yi j cross fik, and we sum it over with I going from 1 to n cross Fik, and then we will have sigma j is equal to 1 to m Cj. Is this line clear? See, in most of the practical systems you will come across, maybe the couple part will not be there in the original system. We'll only have parallel forces. So we have found the resultant at any one point, and let's say we have found them at the origin. So now the resultant consists of two parts. Now what do we find? What is the direction of this couple? The net resultant couple we see, when I take I cross k, I will get a j component. When I take a j cross k, I will get an I component. And all these Cj's are only along I and j directions. That means the net resultant Cr for this system is along I and j directions. So now what I can do is I can shift the system from origin to a specific point, and this point now is a single point. It is not a line of action. Let's say it is x bar y bar, such that Cr about this point, and again I'll specify this, x bar y bar is equal to 0, and therefore at the point x bar y bar, the equivalent force system is a single force Fr, and there is no couple which comes associated with this force. So that is how we can express a system of parallel forces, and it may include couples also which come because of parallel forces, to a single force Fr. But now the catch is that this has to be at this specific point x bar comma y bar. Practically, how do we find x bar y bar? So then the question comes, practically, how to find x bar y bar, and we will use the same method which we used at the end of the last class to find where the equivalent acts for a planar force system. That means we will find, firstly we will find the Cr about origin. So we will choose some origin and we will find Cr about origin of the original system. Next we will say, let Fr alone be the equivalent at x bar y bar. So, and let this, in first part, whatever Cr we have found about origin, let that be Cr comma O. I'm just defining this property. Now if Fr be the equivalent at x bar y bar, then what we have is the, if we take the moments about origin, then we will have x bar I plus y bar j cross Fr. This will be the moment of the equivalent force system, and this must be equal to Cr at O. And this equation, this will give us two scalar equations. Why will it give us two scalar equations? because Fr, the direction of Fr is k. So when I take I cross k, I will get a j component. J cross k will give me an I component, and this resultant Cr will have an I component and a j component. So we equate I component and the j component, and this will give us x bar and y bar both. Now, often when I do this topic, students ask this question, that when we have a planar force system, then we find the equivalent force. We say it intersects x-axis at x bar or y-axis at y bar, and we find only one of these. But in a parallel force system, we find Fr, which acts at x bar comma y bar, and now we have to find both x bar and y bar. And here I would like you to think why this happens. I've already given you the answer to this, but you should think about this, that why are we doing it like this for planar force system, whereas for parallel force system we are finding both x bar and y bar. Just think about it. The answer is quite straightforward, has been given earlier, but if you can't, then we will discuss this at the end of the, or in the discussion part which we take up, we will have a look at this. So these are the two types of force systems we have done. But one thing we have to mind, even for parallel force system, if we have a force system where the resultant force is 0, that means sum of all the parallel forces which are acting at different points, they come out to be 0. Then in this case, the equivalent system is either a couple which is equal to CR, and this couple now will be the same about all, just a couple not associated with any force, or the other case will be, even if CR is 0, then in addition to FR being 0, then this would be a case of what we call as a null system. That is, effectively there is no effect of this force system on the body, there is no couple, all the couples are cancelling out, all the forces are cancelling out. That means all these forces will cause no effect on the rigid body considered as a whole. Okay. So far all these equivalents which we have done, we have seen these for discrete forces, discrete couples. Now the same argument can be extended to distributed forces. What do we mean by a distributed force? How is it different from a discrete force? A discrete force acts at a point, whereas a distributed force acts either along a line or a surface or along a volume. So distributed force is a continuous function. I will draw a figure to make these things clear, but a distributed force will act either along an area or along a volume, but the discrete force acts only at a point. And sometimes, depending on the physical problem we have to analyze and we assume a force to be discrete. Actually, if you think of it, in real life, hardly any force will be discrete. Let us say I'm applying a force with my hand, with my finger on my hand. Now, how do I assume? What do I assume this force to be? Is it discrete or is it distributed? And the answer to that will depend on what my application is. If I am going to study that when I press my palm with my finger, if I want to study the local deformation on the palm, then I will concentrate on the region where my finger is acting. And therefore, the force which the finger is applying on the palm, when I magnify this region, study this. This is a distributed force. All points on the fingers are applying a force, and I am going to study that. But if in the same example, I just study the finger is applying a force on my palm, I want to study the total palm. Then with respect to the total area of the palm, the part of the finger which is touching the palm is a very small area. And if I want to analyze the total palm, I'm not interested in local deformation where the finger is applying a force, then I will treat this as a discrete force. So therefore, actually, as you see from this example, it will be very difficult to find examples of forces which are actually discrete. But depending on our applications, even a distributed force, we treat it as a discrete force. So now we will talk of distributed forces. And earlier here, without explaining, I have introduced three types of distributed forces. A distributed force which acts along a line, a distributed force which acts along a surface, and a distributed force which acts along a volume. So let us explain these in details. A distributed force which acts along a line. This force, that means there is a, let us say what we call as beam, there is a single line element on which force is acting, and this force is continuously acting at all points, and this need not be constant, it could vary. So now here, this force is what we call as a distributed force. I use the symbol F sub L. The unit of the distributed force here, and this, let us say I write this function as W of x. This distance is x. So whatever this force is acting, when I say W of x, this will be some function. The units of this will be newtons per meter in SI units, because it is force per unit length. So now let us say we have a force where W of x, this could have any shape. Let us say this is equal to x square. So that means I have a line element where this distance is x. On this, a force is acting which is equal to x square. Now here, if I say this is x square, that means I am choosing my y direction like this. It's downwards. The force is acting along the y direction and it is equal to x square. Now what does this mean? That it is varying in a quadratic way. At x is equal to 0, W of x is equal to 0. At x is equal to 1, W of x is equal to 1. So the force is 0 newtons per meter at the origin, and at x is equal to 1, this becomes equal to 1 Newton per meter. And if I want to find this force, or what is the intensity of this force at x is equal to 0.5, so then this will be equal to 0.5 square, so that will be equal to 1/4 Newton per meter. So W of x gives me the distribution of this force along the length of the element. Practically, where do such forces come? In civil engineering, we often have elements which we call beam. Beam is an element where the cross-sectional area, the length corresponding to the cross-sectional area dimension is much less than the length of the beam. For example, if we have a circular section like this radius is r, this length is l. So what we will call as a beam would be uh, as an element where this area, now this area will have corresponding lengths. In case of circle, there is only one length, the radius. If this is a rectangular beam, there will be two lengths, L and B, or H and B, and the length element of this structure is much bigger compared to the length elements which are coming in the area. So that is what we call as a beam, and beams come everywhere when we have in roofs. For example, if you see a structure of a roof, you have these beams which are there which take the load, and the load on these beams may not be uniform, it may not be discrete, it will in general be some function which is distributed. So that is how we come across this linear function. So now let's have a look at this. So we have, let's say, a case like this. We are talking of a planar situation, and we have a linear distributed force W of x. Now when I say linear distributed force, please, or distributed, I should probably put it, the distributed linear force. What the meaning of linear distributed will become clear when we take examples of this. So actually what I'm talking of is a distributed force which is linear in nature, and this is given by W of x. So now when this type of situation comes and you have to analyze, let us say, this beam AB, then the question comes, and this is where you will see the advantage of these equivalent forces. What is the equivalent force due to this loading? This is one question which will come, and the second question which will come will be, where does this act? And these questions, what is the distributed force, where does this act, are needed because our equations of equilibrium will contain forces and moments. So let's try to answer this question. What is the equivalent force and where does this act? I'm just posing the questions. So this is X, this is W. So we have this distribution of force and we want to find where it acts. Let us say this is 0 This is L. Now, first of all, we analyze, we see this is a system of parallel force. All the forces are parallel. Now, how do we find the resultant? Fr, if you realize, so far which we have used, this is equal to sigma Fi. This was the case for discrete forces. How will this now modify for a distributed force? What will happen to the summation? And from our knowledge of maths, we know that when we have a distributed force, distributed function, let's even not call it a force, then the summation becomes the integration. So the summation in this case, because the force is continuous, is replaced by integration. That is the basic definition of an integral. A summation of a function gives us the integral. So what we do is, this is what we do in all cases where we have a distributed function, and this will happen not just in mechanics. Any other course, you have electrodynamics, you have distributed charges on a body. Any other thing which we come across in engineering, this principle will be valid. What we do is we choose. So I'll go on a new page. Whenever we have a distributed function, we want to sum upon this. Please get to this technique. We choose an element. In this case, our function is distributed over a line. So we choose a linear element, and a linear element for a straight line case, an element dx. What we mean is that this is basically an element of length delta x, and when we say dx, this means that what we will do is eventually we will take delta x going to 0. When delta x goes to 0, so that is what gives us dx. Now on this, what is the force which is acting? Now this function is given to us as w of x, and this element of length dx is located, so we choose a linear element dx at a distance x from origin. So this is the most basic step. We choose a differential element of dx which is at a distance x from the origin, and once we choose that, then what we find is what is the force on this element dx, and let me write this as d sub f. Let us first work it as a scalar. These are all parallel, so we can make it as a vector later. Now this will be equal to the shaded area which I have shown, because w of x is force per unit length, and because this element is very small, so w of x multiplied by dx is almost like a rectangle. So df is given as w times dx, or maybe I will still write it as, to make it very explicit, w is a function of x, so w of x dx. So this is the force on this element. What is the next step? Dx, this x, dx is located at a distance x away. In this entire range, how does our x vary from? X varies from 0 to L. So therefore, this becomes integral from 0 to L. This will give us the total force. So once I say, in the earlier discourse, we talked of discrete forces. we put a summation sign. Summation sign meant summing over all those discrete forces. Now what I am doing is I am adding up all these small elements. That means I am putting an integral on this. So integral df is equal to integral of from 0 to wx dx, and this is nothing but the total force. So the total force is equal to integral from 0 to L w of x dx. This is a point which everybody has to understand. Unless you understand this, you'll miss out most of the things in engineering. Wherever mathematical applications come in engineering, and this holds irrespective of all branches, we have to do things like this. We choose a basic element, and there we work out whatever is the force or moment or whatever is acting on that element, and then we sum over that, which means we integrate. So next, so this is the total force which comes like this, and we know this force is in the minus y direction or the y direction, depending on where you choose y. Let me pose another question. What is the moment due to the loading about the origin O? So we have this loading W of x. We have to find the moment due to this loading about origin O, and that will answer our second question: where does the force act? So once again, like before, this is repetitive, but we have this function W of x. We choose an element dx at a distance x away. So now this is the shaded part is the force which is acting here. Let me work out what is the moment about origin. So we have to find the moment about origin. What is the moment because of this force df, which is w of x dx? What is the moment about the origin? So now this force is acting here. It is acting at a distance O. So the moment will be equal to x multiplied by df. So this will be equal to x times w of x dx. So this is what the moment is for this particular element. Now all what we have to do is to find the total moment. We have to sum it up. So we do integral dm. This will give us the total moment about origin, and this will be equal to x times w of x dx, with x going from 0 to n. So this is the total moment. And now coming back to the question, what was the effective point of action of the resultant force? First of all, what we found was that the resultant force was equal to integral of w of x dx, x going from 0 to L, and let us say it's a vector, it's in the minus j direction. Now the effective moment we have found out, moment about O, this was equal to integral x w of x dx, x going from 0 to L. Now to work out the direction, this distance x was like this. This is in the minus j direction. So we go from x to y. X is r cross f. So we go, this is the r direction, this is the f direction. That means I'm going, my arrow is going like this, which is counterclockwise. So this, the direction of this, sorry, this is clockwise. So if x and y are like this, then this is x, this is y, x cross y, that gives me a minus k. So this is the moment. And what we will have is the point x bar, where the force Frx. This clearly will be the value of this moment, so I'm not putting the vector sign, divided by Fr. So this will be equal to integral x w of x dx divided by integral w of x dx, x going from 0 to L in both cases. So this is how we get the effective line of action of a force. Now, I think what I'll do is I'll take one or two small examples of this, and then I will leave it open for question. Earlier I was thinking I will, but meanwhile, if you have any questions, please put on your query now. I'm taking up an example for this distributed force, but if there is anything you'd like to ask, you'd like to flag something, please keep on sending your comments. Meanwhile, let me take up an example here. So let's say the two specific cases we consider. First case is what we call a uniform load. So we have a beam like this on which we have a uniform load. Now because this load is uniform, we call it as W0, which is a constant. Now there's one more thing before I move on. What we'll realize is that this force which we have found, which is integral W times dx, this force is actually nothing but the area under the loading curve. Integral W of x dx gives us the area under the loading curve. So area under the loading curve gives you the point where gives you the total value of the force. And if we look at integral x W of x dx, and if I divide this by W of x, so this was the point where the effective force acted. Integral x W of x divided by integral W of x, this actually tells me that the force acts at the centroid of the area. This is the definition of the centroid. So before we take the example, let's generalize and let us give this, that the effective force, let me put these two comments first, then I will come to the uniform loading. The effective force is equal to the area under the loading curve, and it acts at the centroid of the area under the now these two things which I have written, they are useful if the loading is such that the areas can be found without integration and the centroids can be found without integration. But if the areas are complex, then we have to carry out the integration. And in the light of this, let us look at the example which I had started, that if we have a uniform load. Now, what is the equivalent of this? I put three signs which shows equivalent. Then what will be the equivalent of this? What is the area under this curve? The area under this curve is W0L. That means F equivalent is equal to W0L. Notice whenever we have linear loading, the dimension of W, this will be force per unit length. And this is not dependent on the shape of W. W may be uniform, W may be 0, W may be quadratic, W may be sine function. Whatever is the shape of W, its units are always force per unit length. So, and if that means it is newtons per meter, the equivalent force when I say is W0L. So you will see the units come out to be consistent, they would be newtons. Now we have equivalent force is equal to W0L. Then we ask, where does it act? Any answers? Think about it. It will act at the centroid of the area. That means the equivalent of this force system which I have drawn, a single force W0 acting on a beam of length L, will be a single force W0L acting at L by 2 from either end. Is this clear? Let's take the next case which we can find without using integration. So the next case is that of what we call as a triangular load. All these forces are parallel, so this is a load which is starting from 0. It goes to W1 over a distance of L. What is the equivalent force? So equivalent force will be equal to area under the curve. So this will be equal to half times W1 times L, the area of the triangle. And it acts the centroid. The centroid of the triangle is, now this you remember not by length, you think of it as 1/3 from base and 2/3 from tip. So that means if we work this out, I draw the equivalent will be equal to W1 L divided by 2 at a distance of 2L by 3 from the tip and L by 3 from the base. So what this means is, if I have to do an equilibrium analysis of this part, I can replace this triangular load by a single load. Now when we talk of centroids, there is a formula for centroid of a composite area. Suppose I have an area A1 whose centroid is at a position x1 bar, and area A2 whose centroid is at x2 bar, and so on, area AN whose centroid is at xn bar. The question I ask is, what is the centroid of the total area? And total area means we are talking of A1 to A2 plus AN. And those of you who have, this is a simple formula, the centroid of the total area, so we have x bar for the total area, this is equal to summation of individual area times centroid of that area, I going from 1 to n, divided by the area itself. So this is total area, and this is product of centroid multiplied by area and summation of all those. So this is the formula for the composite centroid. So what I'm trying to say is, suppose you have a rectangle, a triangle, and let us say connected to this is a circle. So I can call this as A1, I can call this as A2, I can call this area as A3. And if I have to find the centroid of all this, I'll take the centroid of A1, which will be at the center here, and multiply it by A1. Then this I can do for all components. I've written this for X, I can do this for Y, I can do this for Z. Now The centroid of this will be 1/3 from the base here. So I take the centroid here. The centroid of this is at the center, and then I work out the x component or the y component using formulas like this. So this is the formula for a centroid. Now, this was a small mathematical detour, but let's now go back to this question of loading on the beam. Let's come to the third case, which is slightly more complex. We take a loading like this. What we call as a trapezium loading. Think about it. How do we work? How do we find the equivalent because of this? Let this length be L. Let this be W1. Let this be W2. It is given that the function is increasing linearly from W1 to W2. What we can do is we can divide this first into a sum of two loadings. A rectangular loading, which is equal to W1, plus I can make this as a triangular loading starting from 0 and the end being W2 to W1. Now, this loading will be W1 times L. And this loading, so this is at the center, and this loading will be half into W2 minus W1 times L at a distance of 12/3. So these two have to be now effectively put, and this we can then put it, use the composite formula for centroid, and as you know, this will also be the centroid of the trapezium. I do not know the formula. I don't remember the formula of centroid of the trapezium. I know the basic formula. I don't recall these details. So then what I can do is I can just work it out. We have these two. So I have force 1 acting at a distance x1, force 2 acting at a distance x2. So the total effective force will be F1 plus F2, and it will act at a distance of F1 times x1 plus F2 times x2 divided by F1 plus F2. So effective, let's work it out. It acts at, so total forces for this trapezium loading, this will be equal to W1L plus half of W2 minus W1 times L. And it acts at the force is W1L. We multiply it at the point. So this is from origin. This is very important because then we have half W2 minus W1L, and this acts at a distance of 2L/3. This is the total moment, and this we divided by W1L plus half of W2 minus W1L. So this is where we will get where the effective force acts. I think at least as far as this thing goes, I would like to end at this point, but I'll now be answering the questions which you have. And if you have no questions, then from my side, I will come to some of these your colleges at random and try to interact with you. So do we have any queries from anywhere? No. Okay, so why don't we try to connect to, let's say, GHRCE QEEE, the one at the bottom here. Okay. There's a question. Okay. So BKTIT, yes, please.
Good morning, sir. So you told about discrete force and distributed force. So you said it depends on the reference of the area. We consider it a distributed and or discrete force. But sir, how can we say that every distributed force in reference of area can be treated as discrete force?
No, I said this for a linearly distributed force, a force which varies along a line. So then, see what we showed, what I showed to you in the figure. Let me just get back to that figure. So this is a general, what I wrote was, what I explained this was for a linearly varying force. So maybe we can focus on the camera. If a linearly varying force is acting along a line, then what I said was the area under the loading curve gives the effective force. Possibly your question is, if this force is acting along an area, if this is acting along an area, as would be the case for pressure, then the effective force would be the volume under that loading. So for a linear force, it will always be, because the force is acting along a line. So it will be the area under the loading. Was that your question or was it something else?
Yes, sir, this one, sir. If we take an example of a hammer and a nail together,
Pardon, no, I
sir,
couldn't get
we
it.
are hammering the nail. Sir, if we take the example of a hammer and a nail, we are hammering that nail on a wall. So that is the example of distributed or a discrete.
What? No, if I'm what we see, it depends on your area of application. Suppose you're hammering a nail on the wall and you're looking at the total wall, you want to see what force is applied on the wall, then we will treat this nail for our purposes as a discrete force. But if I'm interested in just studying the effect on the wall at the point where the nail is being hit, so there may be, then treating this nail as a discrete point may not suffice. And I may have to look at the details. So if I have to look at the wall where the nail is hitting and what deformation it is causing to the wall. So then if I blow that area up and if that is my region of interest, then I will have to see on the nail at different points how the force which is coming is distributed. And this is what leads to, when we do mechanics, what we call as complex contact problems. For purposes of our basic course like this, a nail type of a thing which is acting on what we again idealize it as a point, we will call it as just a discrete force. So at least for purposes of this course, a nail hitting a wall will be more or less a discrete force. Not, I gave this example because some of you may like to know what we do in advanced research. And there then, when I have to study this contact and what is going on in this contact, then I can't treat it as a discrete force, but then I have to, basically I have to go at a smaller and smaller level, and sometimes even to the molecular levels. Okay, is that clear? Okay, anyone else now? Okay, then maybe let's connect randomly to one of the colleges. You connect and then I will just talk to them. No, just try to see where we can get. Are we connected? Yeah, okay. So has the class left? It looks like an empty classroom now. Were only 3 people in this class or have the students left? But this is actually then also Dunjunwala has to be told maybe the experiment is not as great as we were thinking. Is there some center where the students are still there? Please respond to me so that I will get back to you. It is really very disheartening. Wherever we are going, we see only 2 or 3 people. Are they only teachers? Are students not there? At least then this feedback has to be given to the people who are conducting this course. So much of some other college. एक दो अगली बार बीच में करेंगे ये चीज. Let's do it at half hour. Remind me, stop me. Because please, okay, let me interact with you. This is which college? Which one? Where this ZAVU? Okay, VPCOE. Can I please talk to you?
Yes, sir.
Hello, can you hear me?
Yes, sir.
Uh, uh, how many people were there in the class when I was teaching?
There are about 20 students, but
Acha, now they have left.
they are, they
Are teachers, you students,
are,
teachers? Now, I would like an honest feedback. Do you think this is helping, or are the students enjoying it, or is it just like they've been forced to sit here?
yes, no, sir. It's helping for students, but there is
It is
exam, so they're left.
okay. I can understand that. So, but are there is there some constructive feedback you would like to give? Something which you think we can do to improve? फिर इसको
No,
कर
sir.
देना.
It is
PC
very.
wants
You
something
are
ना.
explaining very. Hello.
O- Okay, okay. I think I have a query from PC. Let's ask. Let's connect to PC. Yes. Which was the yes? I think they're connected to the green. Yeah. Yes, please. PC. Some problem with the feed. अब तो सभी चलेगा लगता है. Then they probably are not even listening when I am talking. It must be going like, yeah. Maybe they can type. If you can listen to me, please type if there is any query. In fact, the lecture is not equilibrium. That will come in the next class. Okay. Which one? Yeah, I'm trying to see, but ठीक है चलो, I think everyone has. No questions, okay. ठीक है, I think they must have left now anyway.